My next speaker is Enrique from Oregon University. He will speak on heat prediction of the
Yeah, thanks for the opportunity to talk here. So I did change, as some people already noticed, I changed the topic of talk. If you're looking forward to the other talk, I apologize. If you wanna, I'm still happy to talk about it, but I changed my mind. Time will tell. Well, maybe we'll never know whether this was the right decision. But yeah, so I was going to talk about something like a little bit more symplectic and relate to singularity theory, but instead I'm talking about something more like categorical singularity theory. Anyway, so the story kind of starts, as with many things, of the theorem of Valenson, 1978, that if I look at the sheaves O minus n up to O minus 1. Okay, so maybe I should say first, like, this is trying to work with a lot of people. I think I managed to remember everybody, so we're off to a good start. And like the main protagonist in this talk, before I even state, Valenson's theorem is I'm interested in the derived category of some variety. Okay, so this is the bounded derived category. And I'm lying a little bit because maybe somewhat perversely, I'm more interested in the Fukaya category mirror to this thing, but that's how, for now, I'm interested. Okay, so I forget the structure sheet. That these, so the real content of this theorem is that these generate the derived category of projective space as a triangulated category. Okay, and in this range, okay, and you can say a little bit more about the structure that you get here. So you can easily, you compute, okay, maybe the easiest thing is I compute Hom, and when I write Hom, I mean like R Hom or Hom in the derived category. Everything for me is derived. Of two line bundles. Okay, this is not special to this range. Let's just see degree 0. Okay. I'll be over C, although I don't think. If I take Hom between two different guys, and the reason why I put the minus signs here is to make this part of the talk more challenging. Okay, so this is 0 if I'm going from a more positive one to a more negative one. So that means that I is greater than J. So that's the difficult part of this talk, flipping that sign. Okay, and then, in fact, so this is what it means for these things to be what's called an exceptional collection. So they're all exceptional objects, and there's some ordering that morphisms can only go in a certain way. And in fact, here you have even a little bit more. If I take Hom from O minus J to O minus I, in the other region, this is all in degree 0. Okay, I mean, it's true for all I and J in this region, but it's literally 0 on that. So this is what people call a strong exceptional collection. Okay, and so another phrasing of this theorem, I mean, okay, well, I just said that part. These generators full is that these guys are a full strong exceptional collection for the derived category. Okay. And the other thing that I have not pointed out that's nice about this exceptional collection is that they're all line bundles. So in particular, this is not hard to compute. Like, I know, well, in this case, it's particularly not hard, but if you give me some line bundles, it's easier to compute their cohomology than some like random sheet or even some vector bundle. Okay. So shortly after this, I mean, it's reasonable to ask which other varieties have a structure like this, because this is in some sense the simplest way that you could hope to describe the derived category. And Well, as derived categories came like really back into interest, King made this very optimistic conjecture. So I don't know, one class of varieties in which PN fits, and which we've already heard a lot about today even, are toric varieties. And King conjectured after doing some surface cases, if I remember the paper correctly, that if X is a smooth projective toric variety, then this whole story carries over. So then D of X has a full strong exceptional collection of line bundles. Okay, so looks really nice. I mean, toric varieties are you can get your hands on them, and if this is true, then okay, again, I'll have like all these nice properties, and I'll just be computing. If I want to understand the endomorphism algebra of my generators, and thus understand the whole category, I can actually compute it because they're line bundles on the toric variety. Okay, but unfortunately, as I'm sure many of you know, this conjecture is not true. And maybe the whole point of my talk is like going to be how you can fix it using ideas from mirror symmetry, but we're far from that at this point. So unfortunately, this conjecture is false. But okay, maybe I should put no judgment on like whether it's fortunate or unfortunate. Okay, so the first example was by Hill and Perling, and I think it was published at least in 2006. Okay, and then there were many more examples, like Michela had like an infinite family where you can just take actually Pn that's sufficiently high dimension and blow up 2 points, and the conjecture fails. So like kind of fails spectacularly. And then it was a conjecture for a little while that okay, well King's conjecture was we should just wrote Fano here. Okay, also false, but I have them gave like infinitely many examples of that. Okay, so so the conjecture is like really false. But okay, so anyway, so how do we proceed? Okay, so I have to give up a little bit. I'm describing dx so nicely for a toric variety. But what could we try to do instead? Okay, well, there is a theorem. I think the same time. Okay, maybe I screwed up, but for some reason I have in my mind the next three things I'm going to state all happened in 2006, but maybe I'm wrong. Okay, so there's a theorem of Kalamata, which I think is also in 2006, but maybe okay, whatever. Let's not get hung up on the date. If I'm wrong, I'm wrong. That d of x. Okay, sorry. So for now on, I'm in this. I'm assuming x is a smooth projective toric, right? Okay, x is not like some arbitrary thing. This has a full exceptional collection. Okay, so I've dropped two things. I've dropped strongness, which may be okay. That's like strongness is like saying if I want to look at the endomorphism algebra, then it's like honestly a non-commutative algebra instead of DG algebra, but maybe we shouldn't get too worked up about that. But I've also dropped their line bundle. Okay. And in fact, like this is not, he doesn't like write down an explicit exceptional collection. It's like an existence result. And we don't know like almost nothing about this exceptional collection. Like we don't even know whether they're sheaves. Like the statement is just that there are some complexes of sheaves that give me a full exceptional collection. Yeah.
How do you show it's false? You just try and or is like some
yeah, so you just try it like you know really well how to compute cohomology of line bundles on a toric variety. And you know how big K0 is, and you just like try to write down sequences that are long enough and you just get them instruction. Anyway, so if I'm more like computationally minded and want to get my hands on this, I don't like this so much. I mean, it's a nice result, but instead, Bondel around the same time suggested another way to think about the derived category of a toric variety.
It was earlier.
earlier.
I think it's solid 4, right?
Well, I don't know.
Earlier.
Like, well, okay, I think that the
2 years earlier.
well, the Oberwolfach note, like the only thing that's written about it,
Yeah, that's
I
the
think is
problem.
the
Yeah.
same.
He
But
didn't write it, but he came up about 2004.
okay, so okay, before my I'm thinking about these. Okay, anyway, or okay, so I'm gonna omit the suggestion. Following that, I'm gonna omit the date. But so there's this infamous Oberwolfach note that Bondel wrote about this. He never wrote the paper, so that's why I'm just gonna kind of like write it. It's like Bondel's vision is that you should think about d of x in terms of a stratification on a torus. Okay. So this is a real torus. So this is like, I mean, if you don't like the torus, like this is the M is the character lattice of my toric variety, but if you like, just ignore that. This is a real torus, the same dimension. Okay. So here I'm going to give a little bit more detail. So what does this mean? Okay. So I take a fan. Fan of my toric variety, and for every ray in this fan, so the one-dimensional cones, it has a generator. I get a function pairing with u rho. Okay, so u rho is the generator of the primitive generator of this ray. That gives me a function on this torus. That gives me a function on MR. It descends to a circle valued function on the torus. Okay, if I change my MR element by an element of M, it changes the output by. Okay, and then the Bondel stratification. If I can spell, is induced by the hyperplanes that these cut out. Okay, they're sub-tori, but okay. So if I take this, the inverse image of 0 and R mod Z, or in other words, I just look at the periodic hyperplane arrangement up here given by these, and I pass it down. Okay, so
This is the same technique model of the whole of this facets.
sorry, what?
I mean, my words, for it, you have the dozen top, and for each facet, you have a puzzle index 2 holomorph. This will take just the boundary of them. Intersecting.
Probably that's right, but I mean, this is like, but for me, I mean, but here, I'm not going to use anything like X is totally B side. So like, I'm not going to use any simplicity.
Right. But you're taking a real close.
It's a dual terms.
Yeah, this is the mirror. This symplectic geometry is happening here. But
Yes.
but there's no polytope there because I'm not going to compare that. Anyway. Okay, so okay. What else do I want to say? And okay, I'll do an example in a second, but and for any point in this torus, I'm going to associate a line bundle that only depends on its stratum in here. I get a line bundle of d theta. Okay, so I'm going to write you a divisor, but I'm going to say like the line bundle only depends on its representative here, where d theta is okay, it's the sum of over some toric divisors, as I usually would present such things. Now I'm going to write you some funny coefficient. I'm going to take minus, because of conventions, theta, and I'm going to pair it. I wrote it the other way. Okay. Maybe I should be consistent. with u rho. So theta is an element in the dual, u rho is the element. I just pair these two together, and I take the minus and I take the floor, right? Because this is a real thing. So, and this gives me some development.
Can given the
I'm going to do an example. And just let me write one more piece of notation. I'll write the so then capital theta is the set of these theta, such that theta is in the torus. This is called the Bondel-Thompson collection. Okay, so this is a set of line bundles on my toric variety. Okay, you might ask, like, what Thompson has to do with anything, right? So the way that I presented it is like due to Bondel until it appears in this over-Wolfach note. But before that, the same set of line bundles that appears first in a paper of Thompson, where he's computing like and Bondel had realized this as well, but he's computing the Frobenius push forward of the structure sheet on a toric variety. These are the summands. So Thompson was working in the arithmetic case, but you can do it in characteristic 0 if you want. You take so toric varieties have a Frobenius morphism that lifts the characteristic 0. You just like in the dense torus take everything to the power L. If you push forward the structure sheaf under that, it always splits the direct sum of line bundles, and these are the line bundles that you can get.
So when is this Thompson thing? Approximately 90s, 2000s, 80s?
I think it's the late 90s, but don't quote me on that. It's slightly before Bondel's. At least I emailed with Bondel. Bondel did not object to calling it this. Okay, so let me do an example. Yeah, I'll do the simplest possible example, but hopefully it gives some. Well, maybe not the simplest, but hopefully it gives some idea.
not
Second simplest.
not the P2 one.
I'm gonna do P. I'm not gonna do P1. I mean, otherwise I have to like choose a basis for the card group. Okay, so let's take P2. I will tell you what it is in some other examples later, but and then I will take the fan, which is just like the usual one. So these are my ray generators. These each give me a function. So this is MR mod M. If I take these hyperplanes. So the hyperplane orthogonal to this ray is of course just this guy. If I imagine this fundamental domain, like maybe the origin is here. Then, and okay, because I can't resist, like the mirror symmetry person in me is going to label these with this normal vector. Okay, it's also useful if you think about this formula, because the reason why I have to take the floor is because like these hyperplanes have a normal direction, right? Okay, it matters whether I take the right or it's negative. Okay. So these are the same things as torus. I have this one corresponding to that, and then I have this diagonal that cuts across. Okay, and if you stare at this formula, I mean, it tells you that whenever, like, the line bundle that I get out can never change unless I cross one of these hyperplanes. And in fact, like, it can only change if I cross it in a certain way. So, maybe let me use another color. Okay, so at the origin or at a lattice point, my line bundle is always just going to be O, right? Because if I take it to be 0, then plug in 0 to the formula, I get everything. Okay, if I push up a little bit here, and I take some small theta, well, when I pair with this vector and this vector, I'm going to get a small negative number. I take its floor, I get -1. I pair with this one, I'll get a small positive number because of this minus here. I take its floor, I get 0. So this guy right here is O -2. Okay. Well, as soon as I cross this, the coefficient on I mean, they're all linearly equivalent, but on this hyperplane becomes +1, and so this region gets labeled O -1, and it's actually equal to these ones as well. Okay, so you only get 3, and that's just because like it's always going to be the case if I hit one of these hyperplanes, but the normal is on the other side, then it's the same. Okay, so for Pn, you're always going to get back to Valentin's equation. Okay, so okay, so I've been a little bit vague about what you want to get out of this, but I have some set of line metals. Okay, so now, I mean, in this case, I get back this nice full strong exceptional collection, but as we've already seen, I cannot hope that this is a full strong exceptional collection in general.
I'm trying to visualize this picture for P3. So how many? So you have the cube, right? I mean, in the cube you have how many?
There will be 2 of these.
Two, like the two triangles, right?
There will be 2 triangles, and there'll be like a region in the middle that's kind of like a hexagon, like from one. And that region, and it'll just go up. Well, okay. Maybe it's nicer maybe to put the origin here and go down if this is the negative unit cube. It'll go like O -1, O -2, O -3. Okay. Okay, so what did Bondel write in this overall footnote, like a little bit more concretely? What Bondel claimed is that these generate the derived category still, and that you can like use this torus somehow to think about it. And he never wrote down the proof, but okay, this is not like the main. Okay, but if I want to think about it like closer to Valentin's result, well, Valentin doesn't actually just prove that they generate the category. He gives an explicit resolution for the diagonal involving this exceptional collection, which is better because you can understand how to write a sheaf in this basis. Okay, but following Bondel's ideas and using some more ideas from mirror symmetry, Jeff Hicks, myself, and Oleg Latzarev, I guess it was published in 2024, a couple of years ago, proved that you can resolve. Okay, so maybe here I should be a little bit more careful. So for a smooth toric variety of dimension n. Okay, and I'm simplifying things a little. If you like stacks, this can be a stack. But then there exists an explicit resolution of the diagonal involving these ones. In particular, they generate the category. Around the same time, Jesse Wong and David Farah proved just that part, like using mirror symmetry. We kind of, okay, maybe I should finish. Okay, and this also has the minimum length. So of length n by, I'll write it somewhat softly like this. I mean, you can take sums of these guys, of elements of this form, and resolve the diagonal like that. Okay, so we used ideas from mirror symmetry. We wrote like all our proofs are like entirely algebraic geometric. I don't know, because I wanted to torture ourselves. Okay, so in some sense, you might say, okay, well, they cannot be a full strong exceptional collection, but we still have they still generate the category. We have a nice like explicit resolution of the diagonal that you can actually write down on this torus. Like you just draw a diagram on this torus. So maybe we understand the category and we like call it a day, but obviously I'm not going to do that since I still have more than 20 minutes. Okay, so there are some curious features of this. So one thing, I mean, I didn't explain the constructions. I'm just going to tell you this, but you can see it over here. This collection, everything that I said only depends on the rays of sigma. Right? I didn't use any cone sigma, and in fact, this whole construction only depends. So this Bondel-Thompson collection and the resolution of the diagonal depend only on sigma 1. Okay, and if you see that and you're like sufficiently attuned to toric geometry, well, then you know that the rays of the fan are not something that determines X, of course, but corresponds to like a toric GIT problem for X. Okay, so sigma 1 I mean, maybe determines the wrong word, like correspond, I guess, to X, but rather, your mileage may vary exactly what this means, but rather a finite set of toric varieties.
They're more related by some blobs or something.
Not in general. I mean, sometimes if like they're all toric varieties with the same Cox ring, roughly, or like it's like all it is you take this set of rays and you look at all triangulation that uses a subset. So okay, so if I'm in the smooth reactive case, I can maybe assume.
I mean, you can call them generalized flops, right?
Yeah, okay. You could, but not like an honest flop.
Yeah.
But it's like
Wait,
circuit moves, right?
Yeah, circuit moves, that's all. Okay, so there's some finite set of them. Okay, and these correspond to something combinatorial to okay, so I'm actually only going to take a certain two what do I call it? Chambers or maximal dimensional cones of the GKZ fan or secondary. Okay, so let me just draw the only secondary fan that I like to draw. So for example, like so let's take X, I mean, to be a Herzberg surface of type 3. I mean, 3 is not so important, but I just want to specify some number. And okay, it has a fan that looks like this. And this ray is generated by -1, 3. Right, and these ones are like standard basis vectors. Then the GKZ fan, the secondary fan, has the somewhat unfortunate feature of like when I draw it, it's going to look almost exactly like this cone, although the slopes are different. It looks like this. Okay, so the GKZ fan is always supported on the effective cone of X, and I have two chambers here. This one over here corresponds to my Herzberg surface. If you like geometric invariant theory, it like tells me that like if I take the GIT problem, like the action that this set of rays determines on some big affine space, I choose different stability parameters, I get these quotients. But there are other perspectives too. Or you could also think about in terms of irrelevant ideals if you like. And over here, I'm going to get the weighted projective space P113, okay? Which comes from the fact that the other fan I can build out of this is normal to a polytope, is just erase that. Okay, so Okay, so there is one like subtlety here that you see immediately is even if I start with a smooth projective X, these guys don't have to be smooth, but they'll always be smooth stacks. So really, if you want to keep me honest, I should probably say it, okay? And then I write these as like curly X. Okay, but if you don't like toric stacks, and just, I mean, they're smooth. The fans that you get for the chambers will always be simplicial, so they're smooth DN stack, but ignore that. Okay, so it suggests to us that that somehow this story and these derived categories are sort of, there's some sort of uniform thing sitting over the secondary. And if you try and do like, at least if you try to do like the obvious things, which some of these algebraics that I'm collaborating with tried to do, first you can like glue these, you can try and like glue these varieties of stacks together over their birational locus. That thing has like a horrible derived category. It's like not smooth properly. Okay, so instead, we're going to turn to mirror symmetry to try to solve what we should do. So at the same, meanwhile, so Bondel's proposal had a huge influence on mirror symmetry. And there's a way that you can realize exactly what he wanted as a form of homological mirror symmetry. I mean, I won't get too much into it, but so homological mirror symmetry for toric varieties is like a complicated historical story, but like I guess the first proof of the version that I'm going to state maybe starts with work of Fong, Liu, Troyman, and Zaslow, which realized at least part of Bondel's proposal as a correspondence between the coherent sheaves on X and certain constructible sheaves on this torus. But they couldn't like really they couldn't prove like the totally non-equivariant case. And there was a bunch of work in between, and that correspondence was eventually first like completed by Kuwagaki. And then to actually state it with Fukaya categories, like I'm going to, then I need to also use work of Ganatra, and Chenda, which shows that it is a Fukaya category. There is also a more direct route where you use work of Abu Zaid to do things a bit more geometrically, but then like to put it in to get generation and put it in the context I'm going to state it, you need to do some more stuff, which Jeff Hicks. Okay, so anyway, so now I'll write a very short theorem. So if I take d of x, x is my smooth projective toric variety for simplicity, that this is appropriately equivalent to a Fukaya category, which is on the symplectic manifold, which is the cotangent bundle of this torus that I've been talking about, with some, maybe I should write statement here, with some extra data, which is determined by sigma. Okay, so I will not say much about this because I'm only going to use it for a very brief inspiration, but this is a version of this is a partially wrapped category. Okay, and this is some, and in this context, I need to use Ganatra, and Chenda to even define this thing, but this is some combinatorial stuff. Okay, so roughly what you should have in mind is that this is something that sits in the boundary infinity of this Liouville manifold. It tells me where Lagrangians can't go. That's what we call this stuff. Okay, and
but this stuff is included for the superpotential of the Lagrangian curves.
That's a little bit complicated. So if X is Fano, if you take the Horibapa potential, yes, then this skeleton is a skeleton of this stuff. So like, I think historically, I mean, FLTZ just wrote the thing down. I think, what was it? Ruddat, okay, RSTZ. I forget who's that. Okay, Sibylla, Troyman, Zaslow showed that it's like a topological skeleton. Then Peng Zhao and Gamachenda. So Gamachenda needed some assumptions, but Peng Zhao got rid of them. Showed that this is actually Legendrian, that this retracts on. But it's a skeleton of the natural Liouville structure. But if X is not Fano, it's a little bit complicated. Because the Horry-Baffa potential is not really the right mirror. Okay. Okay, but for our purposes, the important thing, the only thing that I will say is for these over there, so if I take the fans of those guys, if I take the projections, of the stop. So say that these are the fans corresponding to these guys in the secondary fan. These all project to the Bondel stratification. Okay, so the extra data that the fan tells you to get this equivalence is really some data about the extra cones. When I project everything back down just to this torus, then they all project just to this Bondel stratification determined by. Okay. And so now you want to glue these things together. And there's something very simple that you can do on this side, which if I have a partially wrapped Budur category, then I'm actually allowed to put anything here that's a closed subset of the boundary of the stop. So one thing I can do is just take the union. So, okay, so when I've previously given a version of this talk, I wrote that this thing is easy to find and that was objective to somewhat. But okay, if I wrote the category T star MR, I take the union over the stops, the sigma I is, let's say, natural to define. Naturally defined. And if you sort of mess around with it, you get some, you see that it has some nice properties. And I could prove some stuff like directly about this category, but as per my taste, instead, what I'm going to try and do is explain to you what properties this has that you can just go back to the B side, okay? So I'm going to use this as my inspiration and try to construct a mirror. So let's take the mirror construction. Okay, so one thing that GPS, these guys tell me that I can do that, I mean, you have to do some inspection of this data, is that if I take any of these individual guys, they fully faithfully include inside of it. And if I go further, like I could add more stuff. And okay, so anyway, maybe let me just say what to do. So now I'm going to choose any smooth toric stack. Okay, and here I really need to use this stack because of the other things. But if you don't just imagine that everything here is smooth, then it can be a smooth toric braid with proper birational morphism toric. To all of these guys that pop up as chambers in the secondary.
Sorry, why can you do it?
I'll say it in words. But, let me Okay, so if everything was smooth projective, this would just be that I'm taking a simplicial refinement of all their fans. Okay, that's something you so you can just take all their fans together and choose a fan that simplicially refines all of them. That's not so hard. If you do it with if some of them are stacks, you have to be a little bit more careful that it's a morphism. But really, all it involves is you do the same thing, but then you put some root stacks in places so that it'll map down well. So it's like, I mean, it's a totally combinatorial. You're taking a refinement not of fans, but of stacky fans where you have some weight. So it's actually not even very hard. Okay, so suppose I choose such a thing. The reason why I'm asking for these properties, I will not explicitly write it, is if I have such a map, then the pullback on derived categories will be fully fixed. Okay, and so I'm going to define the Cox category of X. And we call it this because it's like depends really only on the braid of sigma 1 or on the Cox ring of X, which is determined by that, to be the category generated by the pullbacks of these DXIs inside of this stuff. Okay, so implicit in here, the way that I've written it is this actually does not depend on this. If I have two of them, I could always refine further and pull back. Everything's fully faithful, I would get the same category. Okay, and now I want to think about these Bondel-Thompson elements in here, so I have to be a little bit careful about what I do with them. And I define if I take one of these elements in the torus, then I have these line bundles related to them. I define O Cox of d theta to be a pullback of one of these. Where I is such that, so I can't just pull it back from any of them. I is going to be the one where this guy is anti-now. So okay, so if you stare at the formula for these, they all have negative coefficients, small negative coefficients if I think about them rationally. So they're all anti-effective. So if I take negative of them, they live somewhere in the effective cone, which is the support of the GKZ cone. And so, the if it lands in one of the chambers, it's NF on that chamber. So where I is such that minus d theta lies in PMI. Okay, and a calculation you can do is that these pullback, if it lies in several of them, like if it lies on a wall in between two, then this pullback is like literally just the same line. Okay, so here's the theorem. This is one person, in case you're going to question my alphabetization skills. Okay, is that the O Cox of these thetas are now full strong exceptional collection of this guy. Okay, so you have this slightly, well, I don't know, slightly varies. You have this bigger category that's not naturally associated to X, but it localizes down to any of the D of Xi. And these line bundles are a full strong exceptional collection. So you can do explicit computation. Okay, maybe I should have go back to my example.
So may I ask if there was in this counterexample some hints about the result like that would hold to this counterexample?
What do you mean? Like, was this like suggested, or like,
Yeah,
or like if you stare, like if you think about, as far as I'm aware, no. I mean, so like the idea to try to, I mean, okay, so it's natural in various ways to try to glue together all the toric varieties from the secondary fan. Like some of these people who do hypertoric stuff, like Nick Proudfoot has this paper called like all the GIT quotients at once. One thing you can do is like birationally glue them all, and then there's actually like some hypertoric variety that's like a little bit nicer than this non-separated stack that you get. I do not know how to relate this to that. It's also not totally clear to me that the obstructions that you get when you, I mean, maybe somebody who was more into it at the time, but the obstructions you get in these counterexamples like look like they have something to do with the secondary. On the other hand, like a lot of the, like, people still like love to, like, this King's conjecture was very popular. People love to just like take some X and figure out whether or not it holds for that one. And almost all the examples you'll find, you're taking like some subset. And it turns out to be an exceptional collection on that toric variety. And there are reasons for that that come. That's the best answer I can give. Okay, so if the only thing I will draw here is if I take the secondary fan, so here's the secondary. These Bondo-Thompson elements, there's 6 of them. Oh, wait. Of course, there's one at the origin. They're like this. And so, like, these ones, maybe I should. So in my recipe up here, these pull back, you have to pull back these from the Herzebruck. You have to pull back these from the smooth stack D113. And then these you can use, these two you can use pull back. Okay, of course, like for instance, the structure sheaf always pulls back. And in this case, like actually both of these varieties have full strong exceptional collections of line bundles in this example, just because I picked like a nice simple 2-dimensional example. And in fact, like the full strong exceptional collection on the Herzebruck, a full strong exceptional on the Herzebruck is these 4. And yeah. Okay. So maybe just in my last like 2 minutes, I will say very briefly how this works. So there are 2 main steps. So first, you have to show that these generate this Cox scatter, right? And so this basically follows from the earlier result that I wrote up. I mean, you have to show that like there's a little bit of work to do here, but the hard part is somehow already done because you have this resolution of the diagonal that only depends on the rays, and therefore it makes sense as an object here. And it pushes forward to the diagonal on all of them. You just have to show that that glues up. So this essentially follows from these HHL results. Okay, so you have to show that that works. Okay, and then to get exceptionality, this is the harder part. You look like you're in good shape, right? Because you've simplified things somewhat by pulling back it where it's anti-nap, and so that makes the cohomology simpler. It doesn't like quite work out that you can like apply just like a cooked up vanishing theorem, or at least like, well, I personally lost a lot of sleep trying to do that. This follows from what we call the push-pull lemma, which now if I take J to be anything, if I take the derived push forward of O Cox of d theta, so all these guys are in the same secondary band, so that you can like identify their class groups. This is equal to OX. Okay. If you, since we're basically out of time, I won't do it on the board, but if you once you have this, you try and check exceptionality and just use a junction, you can check the things. This basically boils down to that. So this is the hard part. And you can, I mean, as with most things about toric cohomology of toric line metals, it becomes some like piecewise linear function problem. You want to show that if a PL function that's like close to a linear function in a precise sense has like sub-level sets with no homology, and you can do it, but as we tried really hard to get it from like any sort of standard thing, it didn't work. So again, like mirror symmetry kind of saved the day here. If I drew some pictures on the mirror, I figured out how we can figure out how to make the argument, but then we were able to translate it back. Okay, so I'll stop.